welcome. Today what we're going to do is we're going to talk about the difference between mass number and atomic mass or atomic weight. Those are the same things. And we're going to go ahead and do some calculations. So to make sure that we're all on the same page, let's go ahead and remind ourselves of some definitions. Yesterday we talked about mass number, and we said mass number is always equal to what? Protons plus neutrons. So there we go. That's what's in your nucleus. That's where the mass of an atom is. Remember the visual that we talked about. You've got this really dense nucleus that has all of the mass, and then the rest of the atom is empty space for the most part. Because of this, you can't have fractions of protons and neutrons. You would always expect this to be a whole number. So that's what we talked about yesterday. And we also noticed that this number is not on the periodic table. And the reason being that what we see on the periodic table is actually a weighted average of all of the mass numbers of all of the isotopes of that element. So let's go ahead and give a definition for atomic weight or atomic mass. Same thing. And what we're going to call that is a weighted average of all isotopes of an element Okay, so a weighted average of all isotopes of an element.
So why do they put that on the periodic table instead of the absolute?
Because there's multiple mass numbers. The question was, why would that go on the periodic table instead of the mass numbers? There's multiple mass numbers out there because there's multiple isotopes out there. So what we're doing is we're getting a weighted average, just be able to have that one value, and that weighted average implies that you need to know that percent abundance. Whatever you have the most isotopes of, you're going to have a greater percentage of that. So we need to know that percent abundance for that. And again, this is on the periodic table. It would be very rare for this to be a whole number. You would expect it to be some sort of decimal, a fraction of it. And then now the question is, well, why is the actual weight of an isotope not a whole number like a mass number? Instead, it's actually always slightly less. So let's go ahead and answer this question. Why is it really slightly less? And the reason is that some of the mass of the protons and neutrons, it goes into the energy that it takes to hold that nucleus together. Because remember, your nucleus, you've got protons and neutrons. So you've got these positives and you've got these negatives. So we need, those positives are all repelling each other. And so we need something holding those positives together. And that's what happens here. So let's write this down. Let's say sum of the mass of the protons and neutrons go into energy to hold nucleus together. Some of the mass of the protons and neutrons go into the energy to hold the nucleus together. Again, we really expect this. Well, this needs to happen because you've got all of these positives in your nucleus and they repel one another. So what we're going to see is eventually we're going to talk a little bit about this. So we are doing a slight conversion of mass into energy. That's what's happening there. And then when we go into the actual calculation for our atomic weight, what does it mean to have a weighted average? Well, how do you guys calculate your grades? Your grades are calculated by a weighted average. If you make a 50 on a test, which is 60% of your grade, that's a lot more devastating than making a 50 on a homework or a quiz, which is 10% of your grade. So it's the same sort of deal. For this, we're going to use a formula, and I'm going to write this fancy formula, but you don't really have to think of it in these terms. But what it is, you've got this big sigma in math. Anybody know what that means? Summation. You're adding everything together. That's all that means. So it's the summation of all of the isotopes So sometimes you just might have 2 common isotopes, other times you might have 5 common isotopes. But what you're going to do is you're going to sum up the fraction of your abundance. So in other words, it's not in percent form, but it's as a decimal. So your abundance times your mass. So by fraction, I just mean you've already divided it by that 100. It's no longer in percent form, it's in a decimal form. You're taking that abundance times your mass. And you're going to do that for each of the isotopes, and then you're going to add them together. Okay, so now that we know what we're doing, let's just go ahead and do some examples. So this is what we need our calculators for. I am going to write all of this out. I realize that when it comes time for doing your homework, you might be able, if you have a chart like this, I'd have to look at your homework a little bit closer. I think lots of times it's given to you in sentence form and not so much in a chart. But I'm going to write this out for you guys. So if we are going through and calculating atomic weight, because what this says, it tells us that we have 3 isotopes of magnesium that occur in nature, and their abundances and masses are listed below. These percent abundances, they have been determined experimentally. From what we know here on Earth, we know what the percent abundance of these things are. So what we want to do is we want to determine the atomic weight of magnesium. What is it that would appear on the periodic table? And notice that here, magnesium 24, well, that means it has a mass number of 24, but remember what we said earlier, it's always going to be, the actual mass is always slightly less, so instead of being 24, it's 23.985, etc. So a little bit of that mass was lost in the process of holding the converting to energy and holding that nucleus together. So here I can look at this and I know that this is magnesium 25, magnesium 26, right? Because we see that the mass is just slightly less. So just kind of recognize that. So now when I go through this math, all I'm going to do is I'm going to take my percent abundance, but not in a percent form. I'm going to put it into a fraction or a decimal. So it becomes 0.7899 times my mass. And my mass is 23.98504. Well, remember our big sigma? What that says is you have to do that for all of them and add them up. So here we're going to continue 0.1000 times 24.98584 plus 0.1101 times 25.98259. Now before you ever even plug anything into your calculator, look. Well, actually, I guess we could look over here. It doesn't matter. Let's look here. It's easier to think about these numbers, the 24, 25, 26. And thinking about your percent abundance. Tell me roughly, you would expect the number to be somewhere close to what? Close to 24. Could it be greater than 24? No, it can't be greater than 24 because we've got, oh, wait, I'm sorry. Yes, I'm looking at it the wrong way. It can't be less than 24 is what I meant to ask. It cannot be less than 24, but it can be, we expect it to be greater than 24. So you should kind of have a feel for that. If you get a number that is way off from 24 point something, maybe close to 25, then you did something really wrong. So make sure that you think about what that number should be. And we'll pause this while everybody's plugging in. Okay, so we have an answer, and I've gone ahead and I've written in red, and you guys are welcome to use parentheses in your calculator, however you want to do this, but if you did it step by step, I wrote in red what those values are. And then the answer in the calculator was a little bit different, but I'm going to round it to 24.31, and then to get full credit, we want to make sure that we attach those units of atomic mass units. So 24.31 atomic mass units. Here is our rule of thumb that we're going to stick with. When calculating atomic mass or atomic weight, round to the hundredths. In other words, 2 past your decimal. And there's a periodic table that I haven't passed out our class version of this yet, but there's one that we're going to use constantly in class. And those atomic masses, atomic weights, those are all rounded to 2 past the decimal, and that's what we're always going to stick with when with plugging in. So just round that value to 2 past your decimal. Okay, so we are going to move on. They are just that easy. Okay, next one. Here we're doing the same thing. It says calculate the atomic weight of zinc using the data in the table given below. Again, these are all, just to make sure we know our terminology, these are all isotopes of one another, because we learned yesterday that isotopes are atoms of the same element. Well, they're all zinc, but they have different numbers of neutrons, therefore different mass numbers. So all we're going to do is we're going to take these, I'm going to cheat a little bit. I am going to say that now this is 0.486, 0.279, 0.047, and 0.188. A little messy, but you see what we're doing here. Now we're just going to multiply these times the mass. If you want, you can go out here and get some values. And then, and I'll just do that real quickly for you. Hopefully you guys are doing this at home. There we go, something like that. I don't know about my rounding. I think I rounded way too much. And it's probably in my calculator it was greater amounts. So just on paper I didn't show you everything. But when you add all of this up, first of all, without even adding it up, look here and think about what a reasonable value would be. Obviously it's got to be somewhere between 64 and 68. If you don't get it between those values, you made a mistake. So always think about those things, because it's easy to punch in a wrong key, really easy to make little calculator mistakes. So don't miss something because you don't catch the fact that you made a mistake. Okay, anybody get an answer? Very nice. So there we go, 65.38, and that's going to be AMU. So that looks really reasonable to me, because we see that we've got the greatest percentage up here, so right around 65 point something. That looks real reasonable to me. Okay, now I think we're going to work in a little bit different direction. And here it tells us the atomic weight. So this is given to us. We see that gallium has this atomic weight. Well, we also see that we have masses of 2 naturally occurring isotopes, and those masses are given to us. They're just 2 of them. We've got 68.9257 and 70.9249. We want to figure out our percent abundance, so we're working in the opposite direction. So when going through this, the first thing we want to do, remember your formula says that your atomic mass, atomic weight, that's what you have over here. So this is given to us. This is going to be equal to our percent abundance times our mass, and then you just add them up. Well, we don't have any percent abundances, but luckily we're only talking about 2 naturally occurring isotopes. Because it's just 2, we can do this math that we're just about to do. And I know you guys have done this before in math. What do you want to say for your first abundance? What do you want to call it?
X.
X. Sounds good to me. Let's call it X. So in this case, I'm going to say, I'm just going to pick my first one right here. And I'm going to call this one is what I'm calling X. So my mass is 68.9257. So we have to add that to the percent abundance for the other one times its mass. What do you want to do for your percent abundance for the other one? Yes. Okay, so they got it. 1 minus X, because remember, let's just make ourselves a note that our total abundance equals 100 if we're talking about percent. Let's say that total percent abundance equals 100. So if you're talking about a total fraction abundance, I'm sure that's I'm not a math teacher. I'm not sure that that's how you phrase that, but your total percent abundance is 100. Your total fraction abundance would be equal to 1. So that's what we're looking at. We know that together these two things are going to be considered, they're going to add up to 1 since we're looking at it in a fraction form. So this percent abundance times our mass, this percent abundance times our other mass, which we have is 70.9249. Just to make sure we're clear, this right here is for gallium 69. This right here is for gallium 71. So now I am going to pause our video while everybody engages in a little bit of fun algebra. Okay, so we have some magic math here that just appeared, and we solve for our x, and you should get 0.603. So now when you truly answer this question, the question is, calculate the percent abundance for each isotope. Be sure that you identify the isotope. Don't just tell me x equals this and 1 minus x equals that. So instead, what you should be saying is your gallium 69 and your gallium 71. So we've got these two isotopes. Remember, when we calculated x, x was for gallium 69. So gallium 69, the percent abundance, we need to multiply that times 100, and we get 60.3%. The other part is pretty easy. You can either subtract this from 1, or you can subtract this from 100, and you end up getting 39.7%. Okay, and last one, we're going to go over this really quickly so that we can go ahead and do our little lab that we have today. And here it says the atomic weight of chlorine is 35.453, and we know that there are only 2 isotopes of chlorine. Again, it's given, so it's the same type of problem, and I'm going to let everybody here work on that while I set it up. Okay, we have finished, and we have our x is equal to 0.7576, which means our chlorine 35 equals 75.76%, and our chlorine 37 has a percent abundance of 24.24%. Nice job. Last thing that I want to mention. If you ever come across a problem where you don't have actual masses given to you, because remember we said that you're always going to lose a little bit of mass. If you ever come across that situation, such as this one example, which we're not going to go through and do, what you would do when you're calculating that atomic weight, you are going to use the fact that it's neon 20, 21, and 22. You are going to use these values as your masses, as your AMU. So it would be this mass times the 0.9092, etc. So if that ever comes about, then that's what you would have to do. Okay, nice job.